Hello everyone, this is Balu. Welcome to my channel Civil Cafe. In this video, I am going to discuss about the comparison between I section and hollow section. Now, before getting into the video, let me brush up the important fundamentals regarding the bending, shear, torsion and also compression. First of all, first thing that is bending. Here you can see this is a bending equation. M by I is equal to E by R is equal to sigma by Y. Where is a M is a bending moment, I is a moment of inertia, E is a Young's modulus, R is a radius and sigma is the bending stress and Y is the distance from the neutral axis to the extreme fiber of the cross section. Now if you rewrite this equation, you can get this bending stress equation, that is M by I by Y. Whatever the I by Y, it is nothing but the section modulus. Then finally you will get this equation, that is sigma is equal to M by Z. Here from this equation, you can come to the conclusion that bending stress is inversely proportional to the section modulus and directly proportional to the Y, that is the distance from the neutral axis to the extreme fiber of the cross section. Next, coming to the shear, FA Y bar by IB. From this equation, you can say that whatever the shear stress, it is inversely proportional to the width of the cross section across the depth of the section. Next, coming to the torsion. Here you can see this is the torsion equation, that is T by J equal to tau by R is equal to n theta by L. Where T is the torque, J is the polar moment of inertia, tau is the torsion shear stress, R is the radius, N is the rigidity modulus, theta is the angle and coming to the L is the length. Now from this equation you can say that whatever the torsional shear stress is equal to the torque by J by R, where J by R is nothing but the polar section modulus. Now from this equation you can say that whatever the torsion shear stress, it is inversely proportional to the polar section modulus and directly proportional to the radius. The compression, whatever the Euler's buckling load, that is pi square EI by LE square, where E is the Young's modulus, I is the moment of inertia and LE is the effective length of the whatever the structural member. Whatever this Euler's buckling load, it is directly proportional to the minimum radius of gyration. Slenderness ratio, it is equal to the KL by R minimum, where K is the effective length factor, which is depends on the boundary conditions of the whatever the compression member. L is the length and R minimum you already discussed, that is the minimum radius of gyration. From this equation you come to the conclusion that whatever the Euler's buckling load carrying capacity is directly proportional to the minimum radius of gyration, and whatever the slenderness ratio, it is inversely proportional to the minimum radius of gyration. If you consider any structural member, it is going to have high axial load carrying capacity when it is having the minimum radius of gyration and also when it is having the least slenderness ratio, and this slenderness ratio is going to decrease whenever this minimum radius of gyration is going to be increased. And I have listed out the whatever the relations which I have got from the bending, shear and also torsion. And coming to the I section, here if you observe carefully, from the first relation, the bending stress is directly proportional to the distance from the neutral axis to the extreme fiber. Here if you consider this is the neutral axis. Here, as the distance from the neutral axis is going to be increased, the bending stress is going to increase. So from the starting, that is 0 to the maximum at the flange end portion. Most of the major bending is going to be taken by the flanges, and coming to the shear, it is inversely proportional to the width of the section. Here if you consider this I section, the width of the section very less in the web portion. So whatever the shear stress, it is going to be concentrated across the depth of the web portion. Next, coming to the flange portion, it is having the maximum width. So whatever the shear stress, it is going to be very, very low. So similarly, coming to the torsional shear stress is directly proportional to the radius. So if you consider a cross section, for example I section, from the center, if you take the distance from the center of this I section across the periphery of this I section, the maximum torsion shear stress is going to be generated at the periphery. That means the torsional shear stress is going to be maximum at the end of the section and it is going to be minimum inside the section. So here you can say clearly that whatever the I section, it is going to be having high flexural strength because of the distribution of the area that is across the flange part, and it is going to have the shear strength also, because whatever the web, it is going to take the shear strength. And coming to the torsional shear stress, in the I section, there is not at all a cross section which is provided at the periphery of the section. So there is no such area in the I section to resist the torsional shear stress. So the problem comes with the I section is, it is not at all having high torsional resistance. So it is not at all preferred in case of whenever the torsion is going to act in the structural element. And also I want to discuss one important thing, that is, for example, if you consider I section, because of the transverse loading coming onto the I section, it is going to undergo major axis bending. That is, here ZZ is the major axis. Transverse loading, you are going to consider the properties related to the major axis only. And if there is any minor axis bending, then you are going to consider the cross-section properties with respect to this minor axis, that is YY. Now, based on the loading intensity, you can adjust the cross-section properties with respect to major axis and also minor axis. But coming to the compression, there is no such advantage for this compression, because if you consider any structural element, for example, it is a structural element, and because of the axial load coming onto this element, the element is going to buckle in with respect to any axis, that may be major axis, that may be minor axis also. That's why steel structure formulas, you are going to consider minimum radius of gyration. Whatever the minimum radius of gyration with respect to both the axes, that you are going to consider in the formula, so that you will be able to derive the weaker axis properties in the compression formula. So that's why. But if you consider this I section, it is not at all having the much resistance with respect to the minor axis. So it is not having appreciable compression capacity. So we can say that whatever the flexure, shear and also compression which is coming with respect to the major axis, it can take loads, but when it is coming to the minor axis, it is not having appreciable capacity. So coming to the compression, it is not having much capacity because of the consideration of the minimum radius of gyration in the whatever the compression formula. And also I sections are subjected to the lateral torsional buckling when there is a lateral resistance are not provided at successive intervals wherever it is required. Next, coming to the hollow sections. Here, if you observe clearly these hollow sections, hence it is having high torsional resistance, because at the periphery of the cross section, you can see the area which is present, so that it can take the torsion in that cross section. And compared to the I section, whatever the cross section area, it is going to be high in case of this hollow section. So that's why generally engineers don't prefer this hollow section in case of flexure shear. They are going to prefer mostly in case of the axial force coming onto the structure, that may be compression or tension, and also in case of the torsion they are going to prefer, because whatever these hollow sections, it is symmetric with respect to both the axes. So whatever the radius of gyration you are going to get, it is going to be equal with respect to both the axes. So minimum radius of gyration is going to be equal with respect to both the axes, which you are going to consider in the compression formula, so that it is having the axial load carrying capacity. Next, coming to the torsion, most of the area is concentrated at the edge of the cross section, so that it can take the torsion resistance. Now, the problem with this hollow section is that it is very difficult to make connections with this hollow section. This is a drawback for these hollow sections. I section is proportioned in such a way that within the least possible area, it can take flexure, it can take shear, it can take axial load also. So this is a perfect section. Can you say about that? Yes, it is a perfect section in which it can carry flexure, shear and also compression. That's why engineers call it as a universal section. And this is regarding I section versus hollow section. If you have any doubts regarding this video, you can comment in the comment section. And also thank you for watching this video. If you like the content, please like the video and also share with your friends who are working in the civil engineering industry or who are pursuing in the civil engineering degrees in the different colleges. Thank you.